Hello, and welcome to this MoveX webinar, which we are proud to bring you in association with our knowledge partner, Electrobit. My name is Jack Hunsley. I'm a special correspondent at Automotive World, and I'll be your moderator for today's session. And the title of today's session is Reducing AUTOSAR Cost and Complexity with EB tresos and NXP real-time drivers. We'll first hear a presentation by Electrobit's Bruno Kleinert and NXP's Daniel Basler before ending with a Q&A session. If you'd like to ask a question today, you can do so by typing it at any time into the Q&A box on your screen. Slides and a recording of the event will also be made available afterwards. But without further delay, it gives me great pleasure to hand over to our expert speakers, Bruno and Daniel. Over to you.
Thank you, Jack. Just an audio check. Everything okay?
Yeah, coming through nice and clear.
Thank you. Good morning, good afternoon, everyone. My name's Danny Basler. I'll be presenting first, actually, today. I work in the marketing team in NXP's automotive processing business line. This, as you can tell, is a joint webinar between Electrobit and NXP, and the focus is very much is AUTOSAR, and it's a story of two halves, both the tools from Electrobit as well as NXP's latest general purpose automotive microcontroller family called the S32K3. So to begin with, I'll actually introduce that processor family and the background to it and talk about the software, the new software supporting it, specifically the real-time drivers software. And then I'll hand over to Bruno, who will go through how that fits in with Electrobit's tool chain and enabling you for your AUTOSAR designs. Okay, next slide, please, Bruno. Okay, so we'll cover an overview of the MCU family and RTD software. And then, as I said, I'll hand over to Bruno to go through motivation for AUTOSAR, an overview of the Electrobit tresos product line, and then he will demonstrate some examples of the NXP real-time drivers software within the Electrobit tresos Studio environment. Okay, next slide, please. And the next slide, please. Okay, S32K3 is the newest member of what NXP refers to as its S32 automotive processor platform, essentially the brand name for all of our 32-bit MCUs and MPUs for automotive applications. It's a very versatile MCU family. It's general purpose, so it applies or can be used in a wide variety of applications. Body control is the main general focus, seats, pumps, actuators, spinning motors, anything like that. But it's also applicable to car access, steering, lighting, or more kind of electric vehicle related applications as well, battery management systems, and can also be used as a kind of peripheral controller, if you will, in an audio amplifier system, an infotainment system, or even in an ADAS system as well. So it's, as I said, it's versatile, flexible, and can be used in multiple environments. And it offers a broad range of performance options into single core and multi-core, including lockstep, a wide variety of connectivity interfaces as well. And these also help make it applicable to applications like zone controllers, which is one of the new and emerging applications within vehicle architectures today, reducing the wiring harness length and therefore weight in the vehicle, a very popular area of investment at the moment. So it goes beyond the traditional kind of simple automotive MCU reaching into a much higher level of capability in terms of safety, security, connectivity, and it's wrapped within a bundle of software from NXP and indeed from Electrobit as well. So finally, like all of NXP's automotive processors, this family, the K3, can also be used in non-automotive applications, industrial, control, aerospace, medical, anywhere that it fits your requirements. There are no limitations to where it is used. Okay, next slide, please, Bruno. Perhaps the easiest way to kind of introduce the S32K3 is in reference or in comparison to the S32K1 family, which has been in NXP has had in the market for a few years now, still very, very new, but since about 2017. The S32K1 was the single core version, if you will, And essentially what we've done with the K3 is extended the range of the portfolio across multiple areas in terms of performance. We've introduced single, multi-core and lockstep core versions, all built upon the ARM Cortex-M7 core, which, as you may well know, is a superset of the instruction set architecture that's used on the M4F and M0 Plus cores that are used on the K1 family. So there's a high degree of compatibility there. And there'll be different flavors, as I said, available depending on your safety or performance requirements, from single to lockstep with additional cores on top. The memory range has also been extended. There will be some overlap between the K3 and the K1. K3 will be from 512 kilobytes to 8 megabytes of flash. And we will start, the first devices that we've qualified have 4 megabytes of flash, but we will extend the rest of the family thereafter. All of the memories, the RAM and the flash, are ECC enabled for functional safety. Security and OTA over-the-air support is also a key area of investment. On the security side, again, we extend the range of what we've had before on the K1 family, moving up to symmetric and asymmetric ciphers, AES 128, 192, 256, and on the asymmetric side, RSA and ECC encryption as well. We can also support a larger number of keys in memory with a secure fixed area of RAM and a variable sized area of flash for key storage, so over 100 keys can be stored. And we also add in side channel protection capability to guard against any monitoring of the EMC profile or other characteristics of the MCU that could be used as a means to access the MCU through a back door. In addition to that, there is a full hardware over-the-air implementation. OTA, we are seeing increasing demand from the vehicle OEMs beyond the kind of traditional applications such as infotainment updates and instrumentation cluster updates. It's going more broadly. So we've got features like read well write memory, independent flash memory banks for AB swap when you securely accept the firmware into the vehicle, having authenticated it and decrypted it into, or decrypted it, then authenticated it into the ECU, and then doing an AB swap between the different memory banks with the option of rollback as well, should there be any issues with the new firmware. So that's a full implementation which connects very well with the security features I just mentioned. On the safety side, there will be options from ASIL B up to ASIL level D, coming from the lockstep cores, of course, for ASIL level D, but there are also many other hardware safety mechanisms, for example, the ECC and the memories, built-in self-test for memory and logic, memory protection unit. There's also a fault collection and control unit, an FCCU module, which essentially gathers all of the inputs from all of the on-chip fault monitors, watchdogs and other ones, and then assesses the fault, the severity of it, and then takes the most appropriate action to either continue operating in degraded mode or trigger an alarm, or indeed shut down the system reset. So there's a full hardware safety implementation. Additional peripherals that have been extended include Ethernet, and that's the only optional feature on the K3 family is the Ethernet controller. All other features are available in the standard or the base level part number. The Ethernet will eventually support up to 1 gigabits per second on the 8 megabyte flash family members. For the 4 megabyte ones or less than 8 megabyte, it's an optional feature with up to 100 megabits per second, excuse me, not megabytes. There are multiple CAN-FD controllers, of course, and a very rich analog and timing IP set in particular for motor control. We also include, will include I3C, the extended version of I2C in future devices. And we carry over, we keep the Flex IO module from the S32K1 family as well. That's a nice little peripheral that offers some flexibility in terms of emulating serial communication interfaces through programmable logic with its own DMA. All of that IP and more is then packaged in LQFP, BGA, and a new technology called MaxQFP, which is proprietary to NXP, and the S32K3 family is the first to include it. It combines a classic gullwing QFP lead frame with a JLEAD or PLCC lead frame where the JLEADs are interleaved between the LQFP or QFP lead frame. So it gives you a much higher pin count for the same footprint area versus a classic or traditional QFP. And that technology has been fully qualified by NXP today for automotive use as per the requirements of AEC Q100 standard. So that's all of the hardware in terms of the family. Next slide, please, Bruno. And this is how it is mapped or constructed across the portfolio. As you go from the left to right side of this slide, you simply move up in terms of, or the core configurations, the number of cores and the core frequencies increase from left to right. So moving from single core to dual core to lockstep versions from between 120 and 160 megahertz core frequency. On this slide, it shows a maximum of 4 megabytes of flash memory, as you can see there in the kind of upper green section. But as I said, we will extend into 8 megabytes versions as well, and all of the information or the technical information on these processors is already on the NXP website. You can see the full data sheet and other related documentation for them. So scalable core configurations, flash memory, ASIL support, and then the I/O count, the number of CAN controllers, the optional Ethernet, serial communication interfaces, and analog and other peripherals scale accordingly across those memory ranges as you go up and down. So all of the IP is the same, of course, within the family, so that it's easy to move between smaller and larger memory versions in the same package or similar packages. The packages themselves are shown down there at the bottom in the green boxes there. What devices do we have currently and in production? So as you can see there from the orange kind of highlighted boxes, so in production today are the K314 single core, K324 dual core decoupled, and K344 lockstep core versions of the or families within the portfolio. And specifically, those are offered in two packages, the 172 Max QFP and a 257 pin MAP BGA. The MAP BGA package has qualified now, and the Max QFP package will qualify in April 2022, but both packages are sampling today and available to order. So that's the full scope, as I said, of the hardware side of the portfolio in terms of the look and feel of it and the compatibility. And there's a high degree of IP reuse between S32K1 and S32K3 families. So if you are using or have used the S32K1 family before, then it will look very similar in many ways. Some of the other IP is new and or comes from NXP's MPC57 power architecture families, where it's been very successful for many years in timers and other features like that. So it's a mixture of IP. So let me move on now to the next slide, please, Bruno. And we'll talk about software specifically, the other side of the story with S32K3. So there are multiple new software products that are coming out which will support or do support the S32K3 family and the S32K1, as well as other NXP processor families for networking and powertrain applications. And the one I want to focus on today is called the real-time drivers, or RTD. And what that is our new package of low-level drivers for both AUTOSAR and non-AUTOSAR application uses or environments. Historically, until now, NXP has served the market in two ways. If you are a developer who requires AUTOSAR, we have provided a package, the MCAL package, the microcontroller abstraction layer drivers, as a licensed software product to you. And then the remaining part of the AUTOSAR BSW basic software you would purchase, of course, from Electrobit. For non-AUTOSAR customers, we have our own SDK software development kit that we have provided historically as well. We still have those, but now we've got a new solution called real-time drivers, which again supports S32K3 and now the S32K1 family as well. And what real-time drivers has been developed to do is to try and address some of the limitations around the kind of classical model where you would have to maintain two separate architectures if you have Autosar and non-Autosar projects. And also to go beyond, we wanted to go beyond the definition of the Autosar standard to be able to support our drivers across all of the processor's IP, as well as supporting things like multi-core, privileged user mode for register protection and other challenges as well, or limitations, and to make the drivers safety compliant but available for Autosar as well as non-Autosar use, effectively a safety SDK, if you will. So RTD is the solution for that, and what we do is we have a new single set of drivers. The drivers are ISO 26262 compliant, like the processor, so they can be used in applications up to and including ASIL level D. And the same set of drivers can be used in Autosar and non-Autosar environments. The only difference is the way the drivers are invoked through either a high-level interface for Autosar or a low-level interface for non-Autosar. The drivers support all NXP automotive processors based on ARM Cortex-M cores, which is the K3 family and K1, and it will also support, or they will also support, other processors, including Cortex-M or other real-time cores, such as the Cortex-R52 that will be on future powertrain processors. So it's a very broad-ranging software driver package that will apply to many new products going forward. The drivers are developed like the processor as a safety element out of context in accordance with the ISO 26262 standard. So we can, or you can use them in ASIL level, up to ASIL level D applications. And we have the full safety documentation set available like we do for the processor. There is an FMEDA document or FMEA available for each safety driver within RTD as well. In addition to that, the drivers are production qualified. In fact, if I'll just move on to the next slide, Bruno, let me do that, please. The drivers are production qualified, so they are SPICE level 3 compliant. They're developed using a SPICE level 3 compliant process, MISRA tested as well, so production grade code can be used in a production environment. In addition to that, we have taken away the licensing cost for Autosar from NXP. So previously you would purchase the MCAL drivers with real-time drivers, that the license fee disappears. So it's free of charge for Autosar or non-Autosar use, which is a considerable significant saving depending on the number of projects, of course, that you want to develop an Autosar application for. In addition, the drivers can be configured using, of course, Electrobit's own tresos Studio environment, and Bruno will do a demonstration and describe all that. And you also have the option to use NXP's own S32 Design Studio IDE as well, our own IDE, which is similar to but different from the Electrobit tresos one. So you can, that now supports also a driver configuration using the S32 configuration tool embedded inside S32 Design Studio. So that's RTD in one kind of straight summary there. If we just jump to the next slide, please, Bruno. And this is what it looks like. As I said, each driver has two sets of APIs that can be used, high level for Autosar or low level for non-Autosar. For Autosar, we're using the 4.4 release, the latest one, and as always, NXP, we issue new releases as the new releases of the Autosar standard come into the market. So within that, the drivers are the high level interface is driven by and defined by the Autosar standard. So the API is the same as the classic MCAL API, and that can be used in Autosar as well as in non-Autosar environments as well, which is something new. And then for the low-level drivers are only available, the low-level interface are available for non-Autosar application use, of course. The drivers, as I said, are integrated within NXP's S32 Design Studio IDE, called S32 Design Studio for S32 platform. And the drivers can be used as well concurrently. You can use both high-level and low-level drivers at the same time, as long as they do not share the same resource. There's no resource conflicts there. As a customer, you would get the source code, examples, demos, and its full drag and drop functionality within the graphical user interface environment for configuration. It's also supported by other compilers from the GNU C compiler and debugger, as well as IAR and Greenhouse. Okay, next slide, please, Bruno. And this just shows the kind of for the high level interface for AUTOSAR use. It's driven by the standard. So as I said, the API is the same as the former MCAL environment, and the drivers are fully compliant with ISO 26X and SPICE level 3. The drivers themselves have been enhanced and extended, as I said, to include complex device drivers. So all of the processor peripherals are covered by drivers, as well as, and those have been enhanced in many areas, as well as complex device drivers for compatible analog ICs from NXP, the power management IC, the Ethernet PHY, the CAN PHY. So it's a full BOM coverage driver set, if you like, bill of materials. The drivers are based on the AUTOSAR 4.4 release, so there's support for multi-core, enhanced security, as well as other functions that come with that. Next slide, please, Bruno. And then for non-AUTOSAR, it's a very similar kind of look and feel in terms of compliance for functional safety, MISRA space level, and MISRA compliance. And then the drivers themselves cover, again, all of the peripherals. There's some optional middleware. There's a LIN stack and TCP/IP stack from NXP that's provided as free of charge reference software if required. And indeed, the FreeRTOS operating system is also part of the kind of wrapper around the drivers for the low-level interface as well. So, yeah, okay. Next slide, please, Bruno. Okay, yeah, this kind of covers what I just mentioned there in terms of application, or excuse me, the wrappers of the examples, the configuration tools and demos that exist for both, for the drivers for use in both environments. Okay, next slide, please. Okay, and this is how the drivers are kind of mapped. The mapping of the drivers and the interfaces. On the left side are the drivers that are defined by the AUTOSAR standard, and the blue boxes indicate the full driver, the driver names as seen by the high-level interface. For example, GPT at the top left there, the general purpose timer. The orange boxes within that then would be the driver names as they are viewed by the low-level interface. Therefore, GPT would include several low-level driver options, the FTM flex timer module, the periodic interrupt timer, PIT, real-time clock, etc. So that's how they will appear depending on the interface that you are using to configure the driver, whether it's AUTOSAR or non-AUTOSAR. And then on the right side are the complex device drivers that are part of the standard AUTOSAR drivers, but offered by NXP beyond that. Next slide, please, Bruno. Okay, so this shows just an example then of the differences between the two interfaces in terms of the configuration and the API. And the example shown there in the code, you can see how to configure a driver for both the high level and then the low level interface. The high level interface is shown first, and the first call is CAN init, and we reference the CAN configuration within that. We don't specify which CAN module it is specifically. That's done by the configuration itself. And then below that, the low-level interface, where we call the FlexCAN IP in it. So we have the name of that specific IP block, and then we select the specific module or instance of it, and then call the parameters for it. So that just shows you, depending on which interface you're using, how the code would appear typically. And as I said, there are demos and examples available supporting the S32K3 and K1 MCUs to help you get started using your evaluation boards today. That's actually my last slide, Bruno. I would just like to, if I can, just jump back a few slides. If I could just go back just to one final point, if that's okay. Just keep clicking back. One more. One more. One more. One more. One more. And one more. Thank you. It was just to mention, ladies and gents, about some of the other software and just specifically how this is available to you. So NXP has, as well as the real-time drivers, safety software, security firmware, and a multi-core management software. All of this, including the Autosar real-time drivers package, are available either as licensed software or as free of charge software, and full details of it are available on the NXP website for you to access. Okay, thank you very much, Bruno. I'll now hand over to you and slide 15 to allow you to present on the tresos tools.
Thank you, Daniel. So I will take over and go to my point where I will jump in. Okay, so hello, I'm Bruno Kleinert, product manager at EB for our Autosar Classic operating systems and also for our embedded hypervisor product. And thanks to Daniel presenting the K3 and the real-time drivers, I will jump over now to the topic that is motivating. Why do we want to use Autosar? Why does it save costs for you? And then guide you through the EB tresos product line products. And I will conclude then the presentation with some screenshots how the real-time drivers are integrated into our development and now into our configuration environment. So yeah, we are now living in times of the software-defined car. So this means an increasing number of applications, functionalities go into cars, and they increase the complexity and the overall lines of code that are now making a car of today's times. So let's have a look at the numbers here and go from the bottom left to the bottom left top. So we see in a typical body controller, there's around 200,000 to 2 million lines of code, which already is quite a lot. But this increases, for example, if we add to the same vehicle a high-end navigation software system, which then increases the number of lines of code to 4 million lines of code. If we add another high-performance controller to that very same car, we're suddenly reaching areas where we have 20 to 50 million lines of code in the car. And let's just estimate these numbers and think of fully self-driving cars at self-driving levels 3 to 5. Then we are at numbers of around 300 to 500 million lines of code inside a single vehicle. So that's quite a lot of code, quite a lot of software inside a car that increases the complexity really a lot by several dimensions. And there are in the middle here 3 dimensions depicted. So there is one dimension that describes the complexity of a certain function. There are standard functions that, for example, have very low complexity. Then we can think of mid-range complexity functions. And there are, of course, functions inside the cars which add a lot of complexity, so a lot of lines of code. In the second dimension, pointing upwards there, we've got either the system or the vehicle's configuration or different variants of the same system or the vehicle itself. So this adds another dimension of complexity going from, different, ranging from different functions of different complexities up to different variants of those functions for different systems or vehicle components and parts. And now you can add, and think of one more dimension that adds complexity. Now you can imagine there are different brands out there in different regions. So this adds one more dimension of complexity, and you need to handle all these configurations of different functions, different systems, and vehicle configuration for different brands in different regions. So what does this result in and mean in terms of thinking of adding a new software function or in double quotes, just adding an update to an existing function. So there's around 40% of effort goes into the development of that new features or updating a certain feature that is already in the vehicle. And it takes up to 60% of maintenance, for the 60% for maintenance and for the integration of that new function or this update of the function. So this is I just want to motivate here with this slide that there's a lot of complexity in there, and we somehow need to be able to tackle and master this complexity. And this is where the automotive open system architecture AUTOSAR standard comes into play. And we've been looking on the previous slide a little bit into the future. Now let's look a little bit to the past, a couple of years back, when we had controllers, or just labeled here as hardware, and there was a certain function to be implemented inside the car, and there was a software. And yeah, at these times back in time, the software was just developed around the, let's call it, buttons and levers of the hardware. And imagine you want to update that function to a new piece of hardware. So you would find yourself re-implementing most parts of that software again. So this means it takes a lot of effort, a lot of time, and of course you would by accident also add new bugs to that software that were not in there before. Since this is known to be an unpleasant task and not really desired, then AUTOSAR comes into play to ease up the porting to new hardware, and it has other side effects and benefits. So the AUTOSAR standard divides the hardware-relevant parts that are ECU specific and separates them from the application software. So they are then made independent from each other, which makes it possible to develop the application software independent of the underlying hardware, so of the underlying controller. And the AUTOSAR defines some glue in between, the glue between the application and the hardware underneath, and encapsulates all these buttons and levers that need to be pushed and pulled inside this AUTOSAR layer. So this has some certain nice benefits, because you can now switch to another hardware, and all you need to do is you just need to update that AUTOSAR layer. And if you buy this from a supplier, well, you actually don't have to do anything yourself, because the supplier already had done the adaptation to the new hardware underneath, and you need to integrate your software on top of the updated AUTOSAR layer. So this means that you can efficiently reuse your software for different projects on different updated hardware controllers. And of course, this saves you costs from, think in terms of how it was in the past. You really reinvented the wheel again and again for each and every hardware. So you become more efficient in developing your application. And of course, if you don't rewrite over and over again, you can refine the software step by step. So then quality of your application software increases too. So this is how AUTOSAR can help you to save costs by reusing applications and increasing the quality. So why would one try to switch or use AUTOSAR? Because it's the answer to your ECU software project development. So AUTOSAR helps you to master the software complexity you've got and to still fit to your customer needs. The AUTOSAR standard provides you standardized and reusable modules that you can, think of the slide before, put on top of the different hardwares from different microcontrollers, and you can still concentrate on solving your challenges and fulfill your customers' requirements, even if they are from different suppliers, or if you're building your software application for a different OEM. If they all use AUTOSAR, you're always compatible to those interfaces. AUTOSAR also helps you to improve the coordination and reduce the development costs. When your project, your software project uses AUTOSAR and your developers follow the AUTOSAR defined methodology and configure the whole AUTOSAR application and AUTOSAR stack underneath, this can greatly enhance the interoperability between different tool chains. So you can reuse your software that is AUTOSAR based with the AUTOSAR interfaces from one project to another, and reuse the tool chains, because you do not need to adapt any interfaces of the software if when you've got all AUTOSAR compliant software and tool chains. Well, and also AUTOSAR also kind of provides you some good feeling, I would say, because AUTOSAR is nowadays a really widely accepted standard. So I just want to provide you here one number, and this is that the top AUTOSAR EM partners, they nowadays contribute to around 80% of the global vehicle production. So it is, you can be sure that it is an accepted automotive standard. Okay, so now we learned what AUTOSAR is, why would want to use AUTOSAR and how it saves you costs. And now I would like to provide a really brief overview of EB's AUTOSAR Classic implementation, our AUTOSAR basic software for real-time applications, which is called the EB tresos product line. Let's have a quick look, so to say, under the hood, where one can find EB's tresos products. Animation. Okay, now we've got it. Okay, if you jump into the car and you look at the interior, you can find, for example, EB tresos products powering the dashboard, or for example, also the head unit. And it is also secure enough to provide functionality for the emergency call functionality. When we look at a body controller of the vehicle, you can use EB tresos products to implement controlling your mirrors of the car, or sensors and actuators, control them inside the doors, or controllers for the seats inside the car. We can switch over to the powertrain. There we see use of EB tresos products for battery management, or you can, for example, also control the gearbox of the car. And it's even possible to build engine control units with EB tresos products. Switching over to chassis controller, one can also use EB tresos products to control the electrical power steering, or you can use it for ADAS domain controllers, and also for sensor systems like cameras and radars. So this is now kind of just that you get an imagination in which scenarios, in which use cases EB tresos products are already widely used in the field, and just to give you an overview where this product comes into play, where this product line comes into play. So let's have a look at or a brief overview of what is inside the EB tresos product line. So let's have a look at this schematic and simplified architecture. Inside one ECU with one microcontroller underneath, you can see it at the bottom. And to actually use it, you can have the options of two operating systems that we provide from EB. There we've got one product which is called the EB tresos AutoCore OS. It is a single and multi-core capable operating system that is targeting quality managed up to ASIL-B use cases. And they have got an alternative operating system. It is called the EB tresos Safety OS, which is also a single and multi-core capable operating system that is mostly targeting the areas from ASIL-B to ASIL-D, Bravo to Delta levels. For the general AUTOSAR functionality, so the library functions, we provide a product as the basic software module here in this figure, the EB tresos AUTOSAR, a generic. My apologies, the word generic is missing here in the slides. And depending on the project, if there's safety involved there, we have some modules encapsulated in the safety modules package here. For example, the safety runtime environment or the safety E2E protection. So this is EB tresos safety is a bundle of items that can be purchased depending on your project needs. In order to update the executable image on the microcontroller, we provide the EB tresos bootloader product. So you can update the controller and some kind of glue product between the generic AUTOSAR layer, which is OEM independent. We provide some implementations of requirements for OEM-specific use cases, which is encapsulated in EB tresos solution packages for OEMs, depending on the OEM, where you need to fulfill its requirements. And what I described now is software that is running on the microcontroller inside the car. So this is target software, as we call it. And of course, there needs to be the counterpart, where all the configuration is done. So we offer tooling here, which is called the EB tresos Studio. It is the common and only configuration tool for any kind of product inside the EB tresos product line. So there's only the need to learn one configuration tool. It fits for all products that are inside the EB tresos product line. No need to learn a second tool or anything else there. Okay, to shed some light now on how is this used in practical, or what does the typical workflow look like in your AUTOSAR project when using the EB tresos Studio, which means the EB tresos product line for your ECU project. As mentioned before, there is the configuration tool, the EB tresos Studio. It is running on your desktop computer, where you configure the whole AUTOSAR basic software. So this means the whole EB tresos components that you purchased. And within that configuration is, for example, you specify what is necessary for the application that is supposed to be running on top of this AUTOSAR stack. For example, what does the network look like? Will the application require CAN access? Will it perform communication over Ethernet? So all the configuration bits and knobs, they are configured inside EB tresos Studio for those components and bus systems. And for example, and also to for example, you can configure the memory settings and parameters, and also for the operating systems, as mentioned before, for example, for EB tresos AUTOSAR OS or EB tresos Safety OS. All that is done and set in EB tresos Studio. When you're done with the configuration and you think you're happy and ready to produce the target configuration for your device, you hit the generate button, and then EB tresos Studio generates software, the AUTOSAR basic software. So it generates in part source code, but also configuration files for that source code into a static configuration for the target device. And not to forget, it also produces during this configuration phase configuration information that is supposed to be included in the application, so that it's well known to the applications what the settings of the underlying AUTOSAR classic stack are. So that is the typical workflow of the tool EB tresos Studio in practice. So to point out some highlights of the EB tresos products, what you get when you use the our AUTOSAR Classic implementation, you get an efficient and a scalable AUTOSAR compliant product line and product items for your ECU projects. It is completely and fully AUTOSAR supports completely and fully AUTOSAR with only one single basic software stack, and it is only required to use one single tool environment, EB Tracer Studio, to get this whole stack and all of its items and settings configured. It is all safe and ready for serious production, so you can use it for your for real-time, real-world use. It supports single and multi-core microcontrollers thanks to our operating systems. And we also provide engineering service besides our products. So if your project needs tailoring of our products, we can provide that through our engineering services. And we also provide excellent support through our support colleagues. The benefits for you as a customer is that you can achieve the highest safety levels with our products. So this ranges up to ASIL D. And it saves you effort and valuable money by providing you the AUTOSAR stack that enables you to produce reusable software. You can reuse it from one project to another. It is independent of the underlying microcontroller, so you can reuse the software on different projects and different controllers. And it is safe and reliable, mass production ready software. Okay, and now we're heading over to some kind of evidence that we integrated, as Danny introduced it to us, the real-time drivers. We've got some screenshots from our excellent integration team that were provided to me, showing that we've got integrated the NXP's real-time drivers into our EB Tracer's product line. So what we're showing here is on the right hand, you can see a screenshot of EB Tracer Studio. There's one project opened in there that is leveraging the real-time device drivers, and it is targeting, as mentioned by Danny, the S32K3. And you can see highlighted here that we have selected this certain microcontroller in our Tracer's toolchain. These are called subderivatives of microcontrollers. So here we see that S32K344 microcontroller subderivative is selected for this project. This is screenshot shows the modules that are coming with the real-time drivers and which are inside there. It is still called MCAL here, as we learned before. The real-time device drivers, they resemble the interface of an AUTOSAR compliant MCAL. It is compliant here to AUTOSAR version 4.4. We can see that there are modules, AUTOSAR modules in there, for example, for the analog digital converter, the general purpose timer, the input capture unit, pulse width modulation, and the serial peripheral interface. So these interfaces here are all available and shown that EB Tracer's Studio has recognized them, that come with the real-time device drivers. So they are available for configuration inside EB Tracer Studio and available for code generation and configuration generation for your application software. This is another screenshot that shows how to set some parameters of the real-time device drivers. For example, it's a little bit tiny here, but hope you can I can tell you what is here. You can set here in for the microcontroller platform the fast internal clock here and the slow internal clock values here accordingly. So to set parameters inside the microcontroller and to affect its clocking, its internal clocking. And we've got one last screenshot here that is showing the configuration of the input-output ports of the S32K3 with the help of the real-time drivers. We can see here that ports are configured as input ports here, not as output ports, but as input ports. So it is possible to configure all these settings that are available and integrated into the real-time device drivers. They are ready to be used here inside EB tresos Studio. So if you want to use AUTOSAR classic software on the S32K3, and if you want to take the best of the NXP's real-time device drivers, you can access all these functionalities and things inside EB tresos Studio that comes with the EB tresos product line. So yeah, this is how I would like to conclude my talk then. That's the last slide here. So we're now open for questions. Thank you very much.